This is a journal of me studying the iconic programming book, the C Programming Language by Kerningham and Ritchie. It's more of a journal for myself, so I don't know if other people watching this will get anything out of it, but let's begin. So, Chapter 1. A tutorial introduction. Let us begin with a quick introduction in C. Our aim is to show the essential elements of the language in real programs, but without getting bogged down in details, rules, and exceptions. At this point, we are not trying to be complete or even precise, save that the examples are meant to be correct. We want to get you as quickly as possible to the point where you can write useful programs, and to do that, we have to concentrate on the basics: variables and constants, arithmetic, control flow, functions, and the rudiments of input and output. We are intentionally leaving out this chapter features of C that are important for writing bigger programs. These include pointers, structures, most of C's rich set of operators, several control flow statements, and the standard library. This approach and its drawbacks. Most notable is that the complete story of any particular feature is not found here, and the tutorial, by being brief, may also be misleading. And because the examples do not use the full power of C, they are not as concise and elegant as they might be. We have tried to minimize these effects, but be warned. Another drawback is the later chapters will necessarily repeat some of this chapter. We hope that the repetition will help you more than it annoys. In any case, experienced programmers should be able to extrapolate from the material in this chapter to their own programming needs. Beginners should supplement it by writing small similar programs of their own. Both groups can use it as a framework on which to hang the more detailed descriptions that begin in Chapter 2. 1.1 Getting started. The only way to learn a programming language is by writing programs in it. The first program to write is the same for all languages. Print the words, "Hello World." This is a big hurdle to leap over if you have to be able to create the program text somewhere. Compile it successfully, load it, run it, and find out where your output went. With these mechanical details mastered, everything else is comparatively easy. In C, the program to print "Hello World" is the following. Just how to run this program depends on the system you're using. As a specific example, on the Unix operating system, you must create the program in a file whose name ends in .c, such as hello.c, then compile it with the command cc hello.c. If you haven't botched anything, such as omitting a character or misspelling something, the compilation will proceed silently and make an executable file called a.out. If you run a.out by typing the command a.out, it will print "Hello World." On other systems, the rules will be different. Check with a local expert. Alright, so let's try that. Hello.c. Include standard IO. Main printf "Hello World." So it does give a warning because main does not have a return type specified, but it runs. Now, for some explanations about the program itself. A C program, whatever its size, consists of functions and variables. A function contains statements that specify the computing operations to be done, and variables store values used during the computation. C functions are like subroutines and functions in Fortran, or the procedures and functions of Pascal. Our example is a function named main. Normally, you are at liberty to give functions whatever names you like, but main is special. Your program begins executing at the beginning of main. This means that every program must have a main somewhere. Main will usually call other functions to help perform its job, some that you wrote and others from libraries that are provided for you. The first line of the program include studio tells the compiler to include information about the standard input-output library. The line appears at the beginning of many C source files. The standard library is described in Chapter 7 and Appendix B. One method of communicating data between functions is for the calling function to provide a list of values called arguments to the function it calls. The parentheses after the function name surround the argument list. In this example, main is defined to be a function that expects no arguments, which is indicated by the empty list. The statements of a function are enclosed in braces. The function main contains only one statement, printf hello world. A function is called by naming it, followed by a parenthesized list of arguments. So this calls the function printf with the arguments hello world. Printf is a library function that prints output, in this case the string of characters between the quotes. A sequence of characters in double quotes like hello world \n is called a character string or string constant. For the moment, our only use of character strings will be as arguments for printf and other functions. The sequence \n in the string is C notation for the new line character, which, when printed, advances the output to the left margin of the next line. If you leave out the \n, a worthwhile experiment, you will find that there is no line advance after the output is printed. You must use \n to include a new line character in the printf argument. If you try something like printf hello world new line, the C compiler will produce an error message. Let's try that. So just like this. Oh. Right, it does. Missing terminating quote character. Alright, that's interesting. Printf never supplies a new line character automatically, so several calls may be used to build up an output in stages. Our first program could just have been written like that. Really, hello world. Man. Oh yeah. Cool. To produce identical output, notice that \n represents only a single character. An escape sequence like \n provides a general and extensible mechanism for representing hard-to-type or invisible characters. Among the others that C provides are \t for tab, \b for backspace, \quote for the double quote, and \/ for the / itself. There's a complete list in section 2.3. Alright, first exercise. Run the Hello World program on your system. Experiment with leaving out parts of the program to see what error messages you get. So I think we already did that. Exercise 1-2. Experiment to find out what happens when prints argument string, I think that should be printf. Oh, print s's argument string contains C. Wait. Printf. Print s. What? I don't know. Let's try that. So \c. And then it says unknown escape sequence. Wow. That's a cool exercise. Let's try print s. Warning, unknown escape sequence. Oh, and it didn't produce an it all out. Or did it? Undefined reference to print s. Okay, so it should be print f then. And it just prints C. Alright. 1.2 Variables and Arithmetic Expression. The next program uses the formula the following, to print the following table of Fahrenheit temperatures and their centigrade or Celsius equivalents. The program itself still consists of the definition of a single function named main. It is longer than the one that printed Hello World, but not complicated. It introduces several new ideas, including comments, declarations, variables, arithmetic expressions, loops, and formatted output. Let's try that. Fahrenheit. Include stdio. Print Fahrenheit Celsius table. For far is 0, 20, ... 300. Main. Int far Celsius. And lower upper step. Lower is 0. Lower limit of temperature scale. Upper 300. Upper limit. Step is 20. Step size. Far is lower, while far less than or equal to upper. Do Celsius is 5 times far minus 32 divided by 9. Printf %d %dn far Celsius. Far is far plus step. Okay. Let's hope I didn't make any mistakes. Cool, it works. The two lines, print Fahrenheit Celsius table for far, blah blah blah, are a comment, which in this case explains briefly what the program does. Any character between slash asterisk and asterisk slash are ignored by the compiler. They may be used freely to make a program easier to understand. Comments may appear anywhere where a blank tab or new line can. In C, all variables must be declared before they are used, usually at the beginning of the function before any executable statements. A declaration announces the properties of variables. It consists of a name and a list of variables, such as that. The type int means that the variables listed are integers, by contrast with float, which means floating point, i.e. numbers that may have a fractional part. The range of both int and float depend on the machine you are using. 16-bit ints, which lie between minus 32,000 and plus 32,000, are common, as are 32-bit ints. A float number is typically 32-bit quantity with at least 6 significant digits and a magnitude generally between 10 to the minus 38 and 10 to the 38. C provides several other data types besides int and float, including a character, a single byte, short integer, long integer, double precision, floating point. The size of these objects is also machine dependent. There are also arrays, structures, and unions of these basic types, pointers to them, and functions that return them, all of which we will meet in due course. Computation in the temperature conversion program begins with the assignment statements, lower upper step, which set the variables to their initial values. Individual statements are terminated by semicolons. Each line of the table is computed the same way, so we use a loop that repeats once per input line. This is the purpose of the while loop. While far is smaller than or equal to upper, the while loop operates as follows. The condition in parentheses is tested. If it is true, far is less than or equal to upper, the body of the loop, the 3 statements enclosed in braces, is executed. Then the condition is retested, and if true, the body is executed again. When the test becomes false, far exceeds upper, the loop ends, and execution continues at the statement that follows the loop. There are no further statements in this program, so it terminates. The body of a while can be one or more statements enclosed in braces, as in the temperature converter, or a single statement without braces, as in that thing. In either case, we will always indent the statements controlled by the while by one tab stop, which we have shown as for spaces. So you can see it at a glance, which statements are inside the loop. The indentation emphasizes the logical structure of the program. Although C compilers do not care about how a program looks, proper indentation and spacing are critical in making programs easy for people to read. We recommend writing only one statement per line and using blanks around operators to clarify grouping. The position of braces is less important. Although people hold passionate beliefs, we have chosen one of several popular styles. Pick a style that suits you, then use it consistently. Most of the work gets done in the body of the loop. Most of the work gets done in the body of the loop. The Celsius temperature is computed and assigned to the variable Celsius by this statement. Celsius is 5 times far minus 32 over 9. The reason for multiplying 5 and dividing by 9 instead of just multiplying by 5 over 9 is that in C, as in many other languages, integer division truncates. Any fractional part is discarded, since 5 and 9 are integers. 5 over 9 would truncate to 0, and so all the Celsius temperatures would be reported as 0. This example also shows a bit more of how printf works. Printf is a general-purpose output formatting function, which will be described in detail in Chapter 7. Its first argument is a string of characters to be printed, with each percent indicating where one of the other second, third arguments is to be substituted, and in what form it is to be printed. For instance, %d specifies an integer argument, so the statement printf %d var Celsius causes the values of the two integers var and Celsius to be printed with a tab \t between them. Each % construction in the first argument of printf is paired with the corresponding second argument, third argument, etc. They must match up properly by number and type, or you will get wrong answers. By the way, printf is not part of the C language. There is no input or output defined in C itself. Printf is just a useful function from the standard library of functions that are normally accessible to C program. Behavior of printf is defined in the ANSI standard, however, so its property should be the same with any compiler and library that conforms to the standard. In order to concentrate on C itself, we don't talk much about input and output until Chapter 7. In particular, we will defer formatted input until then. If you have to input numbers, read the discussion of the function scanf in section 7.4. Scanf is like printf, except that it reads input instead of writing output. There are a couple of problems with the temperature conversion program. The simpler one is that the output isn't very pretty because the numbers are not right justified. That's easy to fix. If we augment each %d in the printf statement, if we augment each %d in the printf statement with a width, the number of the numbers printed will be right justified in their fields. For instance, we might say printf 3d 6d var Celsius. Alrighty, let's try that. 6d, no, oh, 3d 6d. Oh yeah. Is that different? Well, I don't have the previous program, so let's change it back real quick. Oh. Oh yeah, so now it's like aligned to the right. All right. The more serious problem is that because we have used integer arithmetic, the Celsius temperatures are not very accurate. For instance, 0 Fahrenheit is actually about 17.8 Celsius, not minus 17. Not minus 17, so the .8 got dropped. To get more accurate answers, we should use floating point arithmetic instead of integer. This requires some changes in the program. Here is the second version. Okay, so what did they do? They changed this to float, and they changed that to float, and they changed the percentages, and they put 6.1 and 3.0. Why do they make lower, upper, and step floats though? That's kind of strange. Alright, so it works. Let's try changing this to int and see if it's different. So that's the exact same, so I don't know why they changed that. This is much the same as before, except that far and Celsius are declared to be float, and the formula for conversion is written in a more natural way. Oh, I didn't even see that. Oh, so they do it like this. 9.0 times like that. Oh, because it's like it matches the formula that they gave earlier, I guess. Okay. We were unable to use 509 in the previous version because integer division would truncate it to 0. A decimal point in a constant indicates that it is a floating point, however. So 5.0 over 9.0 is not truncated because it is the ratio of two floating point values. If an arithmetic operator has integer operands, an integer operation is performed. If an arithmetic operator has one floating point operand and one integer operand, however, the integer will be converted to floating point before the operation is done. If we had written far minus 32, the 32 would be automatically converted to floating point. Nevertheless, writing floating point constants with explicit decimal points, even when, even when they have integral values, emphasizes their floating point nature for human readers. The detailed rules for when integers are converted to floating points are in Chapter 2. For now, notice that the assignment far is lower and the test also work in the natural way. The int is converted to float before the operation is done. The printf conversion specification %3.0f says that a floating point number, here far, is to be printed at least 3 characters wide with no decimal point and no fraction digits. 6.1f describes another number, Celsius, that is to be printed at least 6 characters wide with 1 digit after the decimal point. The output looks like this. Cool. But they're saying here far is lower and then it gets converted to int, but they defined it as a float. So I think they made a mistake. Maybe I have a bad version of the book or something. But okay. The printf, okay, we just read that, I think. Yeah. Okay. Width and precision may be omitted from a specification. %6f says that the number is to be at least 6 characters wide. %.2f specifies 2 characters after the decimal point, but the width is not constrained. And %f merely says to print the number as floating point. %d, okay, then the table, I'm not going to read that out. Among others, printf also recognizes %o for octal, x for hexadecimal, c for character, s for character string, and %% for itself. 1.3. Modify the temperature conversion program to print a heading above the table. Cool. So how would we do that? I think if we just do this, Celsius, Fahrenheit, and then okay, maybe add another tab, I don't know. Yeah, let's add another tab. Oh, that didn't work. Maybe remove this tab and add another tab here. It's kind of sketchy. Maybe. Oh, no, that doesn't look good. Let's add that tab back in. That looks alright. Let's see. Alright. Then exercise 1.4, write a program to print the corresponding Celsius to Fahrenheit table. Okay, so I think if we just copy that program, and then instead of looping over Fahrenheit, we loop over Celsius. And then we have to convert this formula, so I guess it'd be far is 9/5 times Celsius plus 32. Oh, and I made a typo there, so and Celsius is Celsius plus that. Right. I think that should work. So yeah. I hope that's correct. 104 Celsius is 40 Fahrenheit. Let's check that. So 32 Celsius. Oh, let's do 104 Celsius and check. Oh, where was it? Oh, 42 Celsius to Fahrenheit. 107.6. 104. Wait, 104 Celsius to Fahrenheit. Is 219, so we got it wrong, right? Wait. Probably I made a mistake in this formula then, I think. Let's see. Celsius is 5/9 times Fahrenheit. So Fahrenheit is 9/5 times Celsius plus 32. That seems right to me, I don't know. Oh, I do hear far. Oh, no, yeah. Oh, I should swap these around? Celsius. So now 40, wait, is that, no. 40 Celsius should be 104 Fahrenheit. Yeah, that's right, cool. So that works. All right. So we did the exercises. Now, 1.3, the for statement. There are plenty of different ways to write a program for a particular task. Let's try a variation of the temperature on the temperature converter. Cool. So we'll call that Fahrenheit 4.c. Include standard IO. Print Fahrenheit Celsius. Oh, Celsius table. main. Int far for far is 0, far is smaller than or equal to 300, far is far plus 20. Print f percent 3d percent 6.1 f far 5/9 times far minus 32. See if that runs. Alright, that works. This produces the same answer, but it certainly looks different. One major change is the elimination of most of the variables. Only far remains, and we have made it an int. Wait, what? Only far remains, and we have made it an int. Right, all other variables are gone. The lower and upper limits and the step size appear only as constants in the for statement, itself a new construction, and the expression that computes the Celsius temperature now appears as the third argument to the printf instead of a separate assignment statement. This last change is an instance of a general rule. In any context where it is permissible to use the value of some type, you can use a more complicated expression of that type, since the third argument of printf must be a floating point value to match the 6.1f. Any floating point expression can occur here. Alright, so you can put a division, like an operation here, instead of just saying Celsius, is what they're saying, I think. The for statement is a loop, a generalization of the while. If you compare it to the earlier while, its operation should be clear. Within the parentheses, there are three parts, separated by semicolons. The first part, the initialization, far is 0, is done. Oh, that's wrong. Okay, I really have a bad PDF of this book. Is done once before the loop proper is entered. The loop proper? I don't know what that means. I guess that means like the body of the loop. The second part is the test or condition that controls the loop. Far is smaller than or equal to 300. This condition is evaluated if it is true. The body of the loop, here a single printf, is executed. The increment step is executed, and the condition is re-evaluated. Right. As with the while, the body of the loop can be a single statement or a group of statements closed in braces. The initialization, condition, and increment can be any expressions. The choice between while and for is arbitrary, based on which seems clearer. The for is usually appropriate for loops in which the initialization and increment are single statements and logically related, since it is more compact than while, and it keeps the loop control statements together in one place. Exercise 1-5. Modify the temperature conversion program to print the table in reverse order, that is, from 300 to 0. Alright, let's try that. So we just do 300 here, and then we go down, and while it is greater than 0. I think that should be right. Yeah, that worked. 1.4, symbolic constants. A final observation before we leave temperature conversion forever. It's bad practice to bury magical numbers like 320 in a program. They convey little information to someone who might have to read the program later, and they are hard to change in a systematic way. One way to deal with magic numbers is to give them meaningful names. A defined line defines a symbolic name or a symbolic constant to a particular string of characters. Defined name replacement list. Thereafter, any occurrence of name, not in quotes and not part of another name, will be replaced by the corresponding replacement text. The name has the same form as a variable name, a sequence of letters and digits that begins with a letter. The replacement text can be any sequence of characters. It is not limited to numbers. Alright. So we define lower, define upper, Oh, they put some comments behind me. Let's copy that over as well. Define step size, and then they replace those magic numbers. Oh yeah, I guess we're not doing the reverse anymore then. Wait, while far is smaller than or equal to upper, we do far plus step. Is that right? I think so. Yeah, that worked. Cool. The quantities lower, upper, and step are symbolic constants, not variables, so they do not appear in declarations. Symbolic constant names are conventionally written in uppercase, so they can be readily readily distinguished from lowercase variable names. Notice that there is no semicolon at the end of a define line. That's interesting. Okay. A new chapter, sub-chapter, I guess, section. 1.5, character input and output. We're going to consider a family of related programs for processing character data. You will find that many programs are just expanded versions of the prototypes that we discuss here. The model of input and output supported by the standard library is very simple. Text input or output, regardless of where it originates or where it goes to, is dealt with as streams of characters. A text stream is a sequence of characters divided into lines. Each line consists of 0 or more characters, followed by a new line character. It is the responsibility of the library to make each input or output stream conform to this model. The C programmer using the library need not worry about how lines are represented outside the program. The standard library provides several functions for reading or writing one character at a time, of which getChar and putChar are the simplest. Each time it is called, getChar reads the next input character from the text string and returns that as its value. That is, after C is getChar, the variable C contains the next character of input. The characters normally come from the keyboard. Input from files is discussed in chapter 7. From the keyboard. Huh. Alright. The function putChar prints a character each time it is called. PutChar C prints the contents of the integer variable C as a character, usually on the screen. Calls to putChar and printf may be interleaved. The output will appear in the order in which the calls are made. So putChar is like the more rudimentary function then? Or why do you have both putChar and printf? They don't really explain that, I feel like. Okay, 1.5.1, file copying. Given getChar and putChar, you can write a surprising amount of useful code without knowing anything more about input and output. The simplest example is a program that copies its input to its output one character at a time. Include standard IO, copy input to output, first version, min, in C. C is getChar, while C does not equal end of file, putChar, and C is getChar. The relational operator means not equal to. So let's try that. So that works. I guess you could also use it like this, right? with a pipe. All right. What appears to be a character on the keyboard or screen is, of course, like everything else, stored internally just as a bit pattern. The type char is specifically meant for storing such character data, but any integer type can be used. We use int for a subtle but important reason. The problem is distinguishing the end of input from valid data. The solution is that getChar returns a distinctive value when there is no more input, a value that cannot be confused with any real character. The value is called EOF for end of file. We must declare C to be a type big enough to hold any value that getChar returns. We can't use char since C must be big enough to hold EOF in addition to any possible character. Therefore, we use int. EOF is an integer defined in standard I/O, but the specific numeric value doesn't matter as long as it is not the same as any char value. By using the symbolic constant, we are assured that nothing in the program depends on the specific numeric value. The program for copying would be written more concisely by experienced C programmers in C. Any assignments such as C is getChar is an expression and has a value, which is the value of the left-hand side after the assignment. This means that a assignment can appear as part of a larger expression. If the assignment of a character to C is put inside the test part of a while loop, the copy program can be written this way. So they do it like this, right? And then they remove the braces. So it still works. What was it called? Copy. Oh, caps lock. The while gets a character, assigns it to C, and then tests whether the character was the end of file signal. If it was not, the body of the while is executed, printing the character. The while then repeats. When the end of the input is finally reached, the while terminates, and so does main. And so does main. This version centralizes the input. There is now only one reference to getChar and shrinks the program. The resulting program is more compact, and once the idiom is mastered, easier to read. You see this often. It's possible to get carried away and create impenetrable code, however, a tendency that we will try to curb. Curb, that's a strange word. The parentheses around the assignment within the condition are necessary. The precedence of exclamation equals is higher than that of equals, which means that in the absence of parentheses, the relational test not equals would be done before the assignment equals. So the statement is equivalent to, alright, so it's right associated. This has the undesired effect of setting C to 0 or 1, depending on whether or not the call of getChar returned end of file. More on this in chapter 2. Verify that the expression getChar EOF is 0 or 1. Okay, how do we do that? Let's call it not equal print getChar not equal. So oh, I guess I should write it like that. Main I guess that would be a number. Like that. Or maybe we'll do it. Yeah, we could have just kept that while loop. Because if I just do it with one character, it will never be end of line, I think, so. Okay, let's do that. Or maybe, okay, maybe we'll just not do it, we'll just do it like that. Or, okay, let's try that. So it's 1, it can be 1 apparently. But how are we gonna, maybe if I just do, oh, yeah, no, then it has a new line, right? So maybe if I do it like this, echo nothing, no. I don't know how you make that say 0 then. Maybe if we just do that. Yeah, okay. So it is 0 or 1. Exercise 1.7. Write a program to print the value of EOF. Okay. Oh. Print EOF main. So I guess it's an integer then, right? So we just do this. -1. That's cool. Okay, next section. Character counting. The next program counts characters. It is similar to the copy program. Include standard I/O. Count characters in input. First version. Main. While get car. Oh, this is not end of file. We increase NC and do this. LD. So I guess LD is for printing along. So what are we doing? So we're just keeping a counter for every character that we get, and then we print that out. Yes. So okay, so it works. That's cool. The statement ++NC presents a new operator ++, which means increment by 1. You could instead write NC is NC plus 1, but ++NC is more concise and often more efficient. There is a corresponding operator negative to decrement by 1. The operators ++ and negative minus I should say can be either prefix operators ++NC or postfix operators NC++. These two forms have different values and expressions, as will be shown in chapter 2, but ++NC and NC++ both increment NC. For the moment, we will stick to the prefix form. The character counting program accumulates its count in a long variable instead of an int. Long integers are at least 32 bits, although on some machines, int and long are the same size. On others, an int is 16 bits with a maximum value of 32,000, and it would take relatively little input to overflow an int counter. The conversion specification LD tells printf that the corresponding argument is a long integer. What happens if we just not say the L here? Oh yeah, because we removed the L. So I guess it doesn't matter for small values. Maybe it matters if the longer trying to print is longer than an integer, right? I don't know. It may be possible to cope with even bigger numbers by using a double precision float. We will also use a for statement instead of a while. Count characters in input, second version. Oh, main, double, for and c is 0, get character is not in the file. Oh, and c. Okay. So our new program actually is a bit longer, apparently. That's interesting. Printf uses %f for both float and double. .0f suppresses the printing of the decimal point and the fraction part, which is 0. The body of this for loop is empty because all the work is done in the test and increment parts, but the grammatical rules of C require that a for statement have a body. The isolated semicolon, called a null statement, is there to satisfy that requirement. We put it on a separate line to make it visible. Before we leave the character counting program, observe that if the input contains no characters, the while or for test fails on the very first call to the get car, and the program produces 0. This is important. One of the nice things about while and for is that they test at the top of the loop before proceeding with the body. If there is nothing to do, nothing is done. Even if that means never going through the loop body, programs should act intelligently when given zero-length input. The while and for statements help ensure that programs do reasonable things with boundary conditions. Line counting. The next program counts input lines. As we mentioned above, the standard library ensures that an input text stream appears as a sequence of lines, each terminated by a new line. Hence, counting lines is just counting new lines. Include standard IO. Count lines in input. And what is that? Is that a 1 or an L? And it's probably an L, man. Number of lines, yeah. While C is get character does not equal end of file. The body of the while now consists of an if, which in turn controls the increment. The if statement tests the parenthesized condition, and if the condition is true, executes the statement or group of statements in braces that follows. We have again indented to show what is controlled by what. This is weird, like, I would never write this without braces. But since this if statement is really only one statement, I guess you don't need the braces. That's interesting. So it works. The body of the while now consists of an if. Oh, I've already read that. The double equals sign, equals, is the C notation for is equal to, like Pascal's single equals or Fortran's ek. This symbol is used to distinguish the equality test from the single equals that C uses for assignment. A word of caution: newcomers to C occasionally write equals when they mean equals equals. As we will see in chapter 2, the result is usually a legal expression, so you will get no warning. A character written between single quotes represents an integer value equal to the numerical value of the character in the machine's character set. This is called a character constant, although it is just another way to write a small integer. So, for example, single quotes A is a character constant. In the ASCII character set, its value is 65, the internal representation of the character A. Of course, A is to be preferred over 65. Its meaning is obvious, and it is independent of a particular character set. The escape sequences used in string constants are also legal in character constants. So, \n stands for the value of the newline character, which is 10 in ASCII. You should note carefully that \n is a single character, and in expressions is just an integer. On the other hand, okay, I think, yeah, this book is really shit, because this should be in double quotes. Is a string constant that happens to contain only one character. The topic of strings versus characters is discussed further in chapter 2. Exercise 1-A. Write a program that counts blanks, tabs, and new lines. Okay, so I guess we can just copy our count lines for count blanks, tabs, lines. Ugly file names, but whatever. Okay. So I guess we'll just do else if C is tab. Oh yeah, and we need to make number of tabs and number of blanks, right? Oh yeah, okay, that was dumb. So if it's set tab, we increment the tab counter. And if C is a blank, so that's just a space, we increase the blank counter. And then in the end, we print lines, tabs, and blanks. So what? That's a really big number. What is that? The tabs? Blanks, tabs, lines. No, lines. Tabs. What? There's 3,000 tabs. Oh, we don't set it to 0. That's why. So that seems to be more like it. I don't know if you can. Okay. So I don't know how we could test if that's right, but we can just maybe echo. Does that work? No. Huh. I don't know how to test that, but I guess we did the exercise. Okay, write a program, so exercise 1-9, write a program to copy its input to its output, replacing each string of one or more blanks with a single blank. Okay, so I guess we had 2 copy programs, right? Oh no, we have 2 count programs. Okay, so we'll just do this and then say replace blanks. So where are we gonna say copy input replace multiple blanks in input by single blank and output. Cool. So how do we do this? Let's put in braces first and then say if C is empty, then we loop, I guess, or get car is empty. Is that gonna work? I don't know. It looks too simple. Maybe we should try something simpler first. Oh. Okay. Oh yeah. So here, I guess we could just do this. Then we do need to assign it here. Like that. Kind of ugly, but oh well. So that works. Okay, exercise 1-10. Write a program to copy its input to its output, replacing each tab by \t, each backspace, by that, each backslash. This makes tabs and backspaces visible in an unambiguous way. Okay, so what are we going to call that? Unambiguous. Oh, maybe we should copy to unambiguous.c. Okay, put it in braces. Then if C is a tab, we're not writing Python. If C is a tab, we put print F then, I guess. This. If C is backslash, we print that. If C is a backspace, is that even possible? A string that has a backspace in it? Oh, I guess, is that like character turn? I don't know. Then we do that. Maybe we should also, doesn't really matter, but, and then else, we just print the normal thing. Alright. It's kind of like a switch statement, but we haven't learned that yet, so. Let's see if this works. Okay, Okay, so it compiles. Now we just try to cat that into it. I mean, it's hard to tell if that's correct, but I think it is. Oh yeah, maybe we should change it. It's just a little detail, but let's call it unambiguous input and output it like that. Okay, so that's done. New section, word counting. The fourth in our series of useful programs counts lines, words, and characters with the loose definition that a word is any sequence of characters that does not contain a blank tab or new line. This is a bare bones version of the Unix WC program. Man, that's cool. So let's call it WC then. Include standard IO. Define in to be 1 inside a word. Define out to be 0 outside a word. So I guess they're doing an enum here, but we haven't learned that yet, so while C's get char not in the file. Oh, forgot a brace. We increase the character count. If C is a new line, oh, I shouldn't put a thing there. We increase our line count. If C is empty or a new line or a tab, stays out. So I guess because we're at the end of a word, oh, I forgot a semicolon. Else if state is out, state is in. Oh, I made a typo. Oh, that's the bug they warned us about earlier. Hey, that's cool. Wow. Every time the program encounters the first character of a word, it counts one more word. The variable state records whether the program is currently in a word or not. Initially it is not in a word, which is assigned the value out. We prefer the symbolic constants in and out to the literal values 1 and 0 because they make the program more readable. I guess they could have just used a bool, right? I mean, or like an int that they use as a bool. But okay. In a program as tiny as this, it makes little difference, but in larger programs, the increase in clarity is well worth the modest extra effort to write it this way from the beginning. You'll also find that it's easier to make extensive changes in programs where magic numbers appear only as symbolic constants. Oh. The line that sets all three variables to 0. This is not a special case, but a consequence of the fact that an assignment is an expression with the value and assignments associated from right to left. It's as if we had written that the operator OR means OR, so the line says if C is blank, or C is a new line, or C is a tab. Recall that the escape sequence T is a visible representation of the tab character. There is a corresponding operator ampersands for and. Its precedent is just higher than or. Its precedence is just higher than or. But we're not using and, so. Okay. Expressions connected by and or are evaluated left to right, and it is guaranteed that evaluation will not stop as soon as the truth or falsehood is known. If C is a blank, there is no need to test whether it is a new line or a tab, so these tests are not made. This isn't particularly important here, but it's significant in more complicated situations, as we will soon see. The example also shows us an else, which specifies an alternative action if the action part of an if statement is false. The general form is that one and only one of the two statements is associated with an if-else if is performed. If the expression is true, statement 1 is executed. If not, statement 2 is executed. Each statement can be a single statement or several branches. In other words, count program, the one after the else, is an if that controls the two statements in braces. Exercise 1-11. How would you test the word count program? What kinds of input are most likely to uncover bugs, if there are any? How would you test the word count program? Just give it a bunch of input with spaces and tabs, I guess. Okay, 1-12. Write a program that prints its input one word per line. Okay. We copy WC to word per line. Or let's just call it WPL. Right, so that prints its input one word per line. So it seems like we don't really need any of these. Do we need state? I think one word per line. So each time we get a space, we just print a new line. Is that what they want? If C is a space, then let's use put car, the new line, and we just put everything. Seems maybe too easy or something. Is that right? It's kind of weird how it's always, yeah, I guess it just does indentation. Yeah, I guess that works then, right? Okay, 1.6 arrays. So let is, so typo, PDF. Let's write a program to count the number of occurrences of each digit of a whitespace character, blank, tab, new line, and of all other characters. This is artificial, but it permits us to illustrate several aspects of C in one program. There are 12 categories of input. So it is convenient to use an array to hold a number of occurrences of each digit rather than 10 individual variables. Here's one version of the program. Okay. Oh, we already have count. What does this do? Counts digits, white space, and others. Let's call it count digits. Include standard IO. Count digits, white space, others, main, and white, and other, digit, so an array, and white is, and other is 0. For I is 0, I is smaller than 10, plus plus I, no digit, I is 0. While C is get car, is not the end of the file. If C, what? Whoa, they don't put all of that in braces? Interesting. Oh. Oh. Plus plus and white else. Oh, magic number there. Oh yeah, we've used 10 all over the place. Maybe we should... Oh, there's only 10 digits, so you would never change that, I guess. Okay, let's compile that. Oh, made a typo apparently. Where is it? Oh, there. That's cool. I guess that works. Oh yeah, they're saying it. The output of this program itself is digits. The declaration int and digit 10 declares n digit to be an array of 10 integers. Array subscripts always start at 0 in C. So the elements are this. This is reflected in the for loops that initialize and print the array. A subscript can be any integer expression, which includes integer variables like I and integer constants. This particular program relies on the properties of the character representation of the digits. For example, the test C is bigger than 0 and C is smaller than 9 determines whether the character in C is a digit. If it is, the numeric value of that digit is C minus the ASCII value of 0. This works only if 0 up to 9 have consecutive increasing values. Fortunately, this is true for all character sets. By definition, cars are just small integers, so char variables and constants are identical to ints in arithmetic expressions. This is natural and convenient. For example, C minus the character 0 is an integer expression with a value between 0 and 9 corresponding to the character 0 to 9 stored in C, and thus a valid subscript for the array and digit. The decision as to whether a character is a digit, whitespace, or something else is made with the sequence that the pattern if else occurs frequently in programs as a way to express multi-way decision. The conditions are evaluated in order from top until some condition is satisfied. At that point, the corresponding statement part is executed and the entire construction is finished. Any statement can be several statements enclosed in braces. If none of the conditions is, I think that should be R, right? Are satisfied, the statement after the final else is executed if it is present. The final else and statement are omitted. As in the word count program, no action takes place. If the final else and statement are omitted, as in the word count program, no action takes place. there can be any number of else-if condition statements. Groups between the initial if and final else. As a matter of style, it is advisable to format this construction as we have shown. If each if were indented past the previous else, a long sequence of decisions would march off to the right side of the page. The switch statement, to be discussed in Chapter 4, provides another way to write a multi-way branch that is particularly suitable when the condition is whether some integer or character expression matches one of a set of constants. For contrast, we will present a switch version of this program in section 3.4. Exercise 1-13. Write a program to print a histogram of the lengths of words in its input. It is easy to draw the histogram with the bars horizontal. A vertical orientation is more challenging. Wow, so they want us to actually create a bar chart. That's interesting. 1-14. Write a program to print a histogram of the frequencies of different characters in its input. Okay. Alright, so let's make a file for exercise 1-13. Count words, hist, like that. Include standard IO. Count words in input and output a histogram. So I guess we start with the main function. Maybe we should peek the other programs, but so let's see. Int, what do they usually call it? C. Int. Let's see. Then we probably also need write a program to print a histogram of the length of words. I guess we also need, let's call it NW, number of words, but maybe call it number of, or just N, maybe, let's just call it N. While C equals get character does not equal end of file, our trusty old while loop. Then let's see, maybe we should use those booleans like they did for counting words. I mean those defines. Okay, so if, let's see, if C is that I, or C is the new line, or something else. Wait, how did they count words earlier? Or tab, okay. Or C is a tab. What do we do then? Then we print the histogram, so I'll just put a comment here. Why does it? Oh yeah, it's not Python. Print the histogram. And set n to 0, I guess. Oh, we don't have to write that in common. N is 0. And otherwise, so we do else C++ or wait, N++, or plus N they wrote earlier, I guess. Is this gonna work? Man, I don't know. So and then print histogram is just going to be it's just going to be a for loop, I guess. For let's create an I variable. For I is 0, I smaller than n, I plus plus, put character, a hash symbol, what? And then we put a new line. I have no idea. Wait, let's read the exercise again. Write a program to print a histogram of the length of words in its input. It is easy to draw the histogram with bars horizontal. Okay, so I don't know. Because let's say there's a bunch of spaces, then I'll just print a bunch of. Maybe we should add here if n is not 0 and that thing. So they said earlier that n has a higher precedence, so I think we need to put this in braces. Let's see if that works. I don't know. So, forgot a semicolon somewhere. Here. So it compiles. So it prints a bunch of. Oh, apparently that was a really long word. I don't know what that is. Huh. Oh, I forgot to initialize. Okay. Wait. What did we call this new file? Count word hist. Do they usually initialize C to something? No. Okay, so we should start with n is equal to 0 then, I guess. Right. Let's see. Count word histogram, and then we cat itself into it. And then it prints a bunch of bars. So for example here, this is like 8 characters, so what word is that then? So that's include, I think. Yeah, it's 8 characters. Okay, so I think it works. Maybe it would be cool if we could print the word in front of it and then print the bar. I don't know. Maybe it's just a waste of time. Write a program to print a histogram of the frequencies of different characters in its input. Okay, that's interesting. How do we do that? Write a program to print a histogram of the frequencies of different characters in its input. I guess so char hist include standard IO. Print a histogram of frequency of characters in input main. So we need a C again, and then we just, I guess we make an array, but then we need to know how big the ASCII table is, right? Or how's that going to work? let's see. Or, oh, well, my internet is out. Where was that? Oh. I guess we could just do the set. So it's gonna use something that they haven't explained yet. We just make an int array of, it's called frick, and it's the size of, no, I mean the biggest character. Did they tell us what that is? Maybe it's I don't know. How do I even look for that? Maybe we could try, oh here. The character counting program. So maybe if we assume what is the biggest character? That's the question. So let's make a little program. Oh, I said IO, yeah. Main. So let's call it car C. And then so if we assume that it is 16-bit, wouldn't that mean that the largest value is 2 to the power of 17 minus 1? So let's see. C is pow. 2, 17 minus 1. Man, I have no clue. And then we print F C, oh wait, 2 values. Then if that is the biggest, then it should wrap around, I think. So we print C and we print C plus 1. Oh, overflow in conversion from double to car. So POW returns a double. Oh wait, they're saying here 127, so I guess that's the biggest for a character? Is that what they're saying? Let's see here. What is that? That is 2 to the power. What is 128? What is the 2 log of 128? 64, 128. 1, 2, 4, 8, 16, 32, 64. So that's 8 bits then. That sounds right. 127, 128. What? So I can just hold 128. So that means it's definitely bigger than what? Or, huh? I don't get it. Huh, okay, so it's definitely more than 8-bit. Let's try, what is the next power to 300? No, 256. overflow. Oh, okay, so we found the limit then. So it's 255, and if we do plus 1, then it's... Oh. Okay. So, well, why is that -1? That's strange. But okay, I think 255 is the size we're after. So, what was it? Character histogram. So, the size should be 255 then. And then we just do our while loop that we've been seeing for a while. C is get character does not equal end of file. Frequency C. Do we do it like this or like before that? Or do we do this? I don't know. So plus means first increment then. So I think it's probably this, right? And then we just loop over. So then we do a for loop. So we need an integer. I is 0, I is smaller than, maybe we should define here. Define max car or something. I plus plus. I mean, it's gonna print a bunch of zeros, so I mean a bunch of line. It's not gonna have every character in it, so I think we first should check if frequency is 0. Yeah, we should do, if the frequency is not 0, then we do our stuff. So if the frequency is not 0, then we do printf, or just put character I think. And then we do a little loop to print a bunch of hash symbols, right? So we need another counter. While j is smaller than frequency of I, j plus plus. This is a really hard exercise. I feel like if you've never done C and this is the first proper exercise you're doing. Put character hashtag, and then put character \n. Here maybe we should do printf. Can you print a character with printf? I don't even know. Let's do 2 statements. Put character, frequency, no, just I, and then we do printf, a space and a colon, or just a space maybe. Like that. So now it's gonna print the character, print a space, and then print the histogram. I mean the bar, right? Let's see if that works. Seems like a very long program not to have any bugs in it. I forgot to declare J here, so that's something. Oh, and I forgot to say that we think that's 255. I'm not sure yet. If it's bigger, does that matter? or smaller. I don't know. Let's see. Yeah. So it has no errors. That's crazy, actually. I would expect that. Oh, and then it just prints a bunch of hash symbols. So there's probably an endless loop in our where we print the hashes. So we need to initialize all of this to 0. How do you do that? I guess we just put a loop in front of it. But damn, that's so ugly. Like that. Oh, and it just prints nothing. Oh, what? What is it doing? So it found 2 exclamations, 3 hashes. So, I mean, it does something. Oh yeah, there's a lot of characters that are not printable, probably. This is what is happening. What is this though? Let's look at the code again. So oh yeah, this should be inside here. Why did I? Okay. Let's see if that works. Okay. Wow, that looks really cool, actually. So, let's see if it's correct here. How do we test that? Maybe with like sed or something, but I don't really know how to do that. So there's a single 2 in the program. Let's see if that's correct. Oh. Yeah, that's right. Okay, so I think it works. Wow, that was a cool exercise. All right, so that took quite a while. Where were we? Arrays. Exercise. Print a histogram of different characters. Okay, so we just did that. Then section 1.7, functions. In C, a function is equivalent to a subroutine of a function in Fortran, or a procedure or function in Pascal. A function provides a convenient way to encapsulate some computation, which can then be used without worrying about its implementation. With properly designed functions, it is possible to ignore how a job is done. Knowing what is done is sufficient. C makes the SU, I think that's a typo, of functions easy, convenient, and efficient. The SU, I don't know that word. You will often see a short function defined and called only once, just because it clarifies some piece of code. So far, we have used only functions like printf, getChar, and putChar that have been provided for us. Now it's time to write a few of our own. Since C has no exponentiation operator like times of Fortran, let us illustrate the mechanics of function definition by writing a function power mn to raise an integer m to a positive integer power n. That is, the value of power 25 is 32. This function is not a practical exponentiation routine since it handles only positive powers of small integers, but it's good enough for the illustration. The standard library contains a function pow that computes x to the y. Here is a function power and a main program to exercise it. Int power. No, that's interesting. They declare it up front. power. Raise base to nth power. Times base. Okay, so they really just define it as repeated multiplication, I guess. Okay, let's see if this runs. Okay. So 2 to the power 3 is 8. Negative 3 to the power 3 is shouldn't that be just 27? Wait, how? I mean, it's probably correct, right? Minus 3. If you do minus 3 times minus 3, it's 9 times minus 3 is minus 27. Yeah, okay. Cool. A function definition has this form: return type, function name, parameter declaration, if any. If any. Oh, okay, so then it can be empty. Declaration statements. Function definitions can appear in any order and in one source file or several, although no function can be split between files. If the source program appears in several files, you may have to say more to compile and load it than if it all appears in one. But that is an operating system matter, not a language attribute. For the moment, we will assume that both functions are in the same file. So whatever you have learned about running C programs will still work. The function power is called twice by main in the line power. Printf power. Each call passes 2 arguments to power, with which each time returns an integer to be formatted and printed. In an expression power 2i, is an integer just as 2 and I are. Not all functions produce an integer value. We will take this up in chapter 4. The first line of power itself, int power, declares the power parameter types and names, and the type of result that the function returns. The names used by power for its parameter are local to power and not visible to any other function. Other routines can use the same names without conflict. This is also true of the variables I and p. The I in power is unrelated to the I in main. We will generally use parameter for a variable named in the parenthesized list in a function. The terms formal argument and actual argument are sometimes used for the same distinction. The value that power computes is returned to main by the return statement. An expression may follow return. Return expression. A function need not return a value. A return statement with no expression causes control. A return statement with no expression causes control, but no useful value to be returned to the caller. Okay. As does falling off the end of a function by reaching the terminating right branch. Right brace, okay. And the calling function can ignore a value returned by a function. You may have noticed that there is a return statement at the end of main. Since main is, there's a return statement. Since main is a function like any other, it may return a value to its caller. Wait, why are they talking about? Oh yeah, have we always written return 0? I mean, that's my own, but like Fahrenheit? No. So, okay. In the interest of simplicity, we have omitted return statements from our main functions up to this point, but we will include them hereafter as a reminder that programs should return status to their environment. Okay. The declaration int power, just before main, says that power is a function that expects 2 int arguments and returns an int. What was it called again? power. Just before, name says that power. This declaration, which is called a function prototype, has to agree with the definition and uses of power. It is an error if the definition of a function or any uses of it do not agree with this prototype. Parameter names need not agree. Indeed, parameter names are optional in a function prototype. So for the prototype, we could have written that well-chosen names are good documentation, however, so we will often use them. A note of history: the biggest change between ANSI C and earlier versions is how functions are declared and defined. In the original definition of C, the power function would have been written like this. The parameters are named between the parentheses, and their types are declared before opening the left brace. Undeclared parameters are taken as int. The body of the function is the same as before. The declaration of power at the beginning of the program would have looked like this. No parameter list was permitted, so the compiler would not readily check that power was being called correctly. Indeed, since by default power would have been assumed to return int, the entire declaration might as well have been omitted. The new syntax of function prototypes makes it much easier for a compiler to detect errors in the number of arguments of their types. The old style of declaration and definition still works in ANSI C, at least for a transition period, but we strongly recommend that you use the new form when you have a compiler that supports it. Exercise 115, rewrite the temperature conversion program to use a function for conversion. Oh, that's cool. Fahrenheit function. Oh, we already have something with it. Oh yeah. Okay. So I guess we're going to do this then. How do we do that? So you here just say convert float. Float. Maybe we should call it convert to Celsius, but that's kind of verbose. Float var. And then we just say return and it returns a float. And then we say here convert to Celsius Fahrenheit. So yeah, that worked. 1.8 arguments call by value. One aspect of C functions may be unfamiliar to programmers who are used to some other languages, particularly Fortran. In C, all function arguments are passed by a value. This means that the called function is given the values of its arguments in temporary variables rather than the originals. This leads to some different properties that are seen with call by reference languages like Fortran or with var parameters in Pascal, in which the call routine has access to the original argument, not a local copy. Call by value is an asset, however, not a liability. It usually leads to more compact programs with fewer extraneous variables, because parameters can be treated as conveniently initialized local variables in the called routine. For example, here is a version of power that makes use of this property.